Okay, so the work we are presenting is entitled QuantumSolver Composing, Automatic Quantum Transformation of Classical Circuits. It has been realized in the University of La Laguna by Daniel Escanez-Exposito, myself, and Pino Caballero-Gil. First of all, we are going to see some context of QuantumSolver. QuantumSolver is a quantum toolset for developers that allows the easy execution of quantum algorithms, and it is divided in modules. QuantumSolver Basic, that offers simple algorithms like Bernstein-Basserani or Deutsch-Jobsa algorithms. QuantumSolver Crypto has several quantum key distributions protocols like BBHE4 or E91, B92. QuantumSolver subroutines allows to run more complex algorithms like Shor or Simon algorithms. And QuantumSolver AI contains quantum machine learning functionalities. The last module, which this presentation is about, is QuantumSolver Composer, that allows simulating classical logic circuits using quantum circuits. Let's see some fundamentals of the proposal. First, we are going to define the classical gates. Not performs a flip of a bit, or is an addition where 1 plus 1 is 1, and is the simple multiplication, and Shor is the addition modulo 2, 1 plus 1 is 0, right? So here we have 4 basic quantum gates that we are going to define by its effects over the basic quantum states 0 and 1, okay? X gate is like a quantum knot, flip the bit. C knot is a control knot. It has a control and a target. When the control is set to 1, then the target is flipped, generating the effect of a quantum short. Swap is a really intuitive gate, just interchanges the state of 2 qubits. And finally, the CC knot gate is similar to the C knot, but using 2 controls. When both are set to 1, then the target is flipped. So why do we need the control as an output of the C knot gate? Let's talk about the reversibility. This property allows us to get the input of a function only seeing its output. Okay, for example, the X gate is reversible because we know that we can apply the knot twice and then we get the input, right? But what about the classical OR? Can we compute the output, but you can restore the input? No, this is impossible because since 3 same values are generated by different inputs, right? So that's why we need to return the control value in the C knot gate to differentiate all cases. Reversibility is a property imposed by quantum mechanics. Okay, so the implemented functionalities are set and reset method to initialize and restore the system, the basic knot, swap, and Shor gates that are inherently reversible, another basic gates that needs ancilla qubits to be reversible, a conditional copy. If a control qubit is set to 1, then can copy a register in another register. And lastly, we have implemented the shifting operation because they are widely used in cryptographic protocols. So to sum up, an exhaustive study of theoretical basis has been carried out. A powerful open source tool has been developed to simulate classical logic circuits using quantum circuits. And some future work that we are already implementing is the addition of new and more complex logic functionalities and the development of cryptographic protocols using this tool to show useful use cases of the module. So thank you very much. And any question? Thanks. Okay.
Anyone? Okay.
Thank you for your talk.
Thanks.
So if I understood correctly, the main part of your work was to implement deterministic gates using reversible quantum gates?
Yeah, right. It's exactly this work. It's used the quantum paradigm to simulate the quantum operation. And you maybe are thinking, and what's the improvement of this of this thing? We are now looking for a way to code the classic information more efficiently using qubits. And then, if we discover this way to encode the information, maybe we, using this tool, can compute better.
And the gates being reversible are a necessity?
Yeah, can you repeat? What?
It's necessary for the gates to be reversible, or?
Are you asking for the reason that must be reversible, or?
Yes.
Yeah. That's a good question. When the quantum mechanics has that a circuit is like a quantum system, and it cannot lose energy, and the information in a quantum circuit is like the energy of the system. And when you has an amount of information at the beginning of the circuit, it has the same energy has to be at the end of the circuit.
Okay. And one final question.
Yeah,
are there any gates which can't be represented by quantum reversible gates?
Okay, that's a really good question. Yeah, of course. When you, for example, measure a qubit, you are destroying the qubit, because imagine you have a qubit that has 80% probability to you get a 0, for example, and 20% probability you get 1. Okay, when you measure, you maybe obtain a 1, or maybe you obtain a 0, and then your qubit, your quantum state, is completely destroyed. So this is it's a gate that destroys the qubit. You lose all your information.
Okay, thank you.
Thank you very much. Another question? Thanks.